Hey everybody, Mr. Gerard here, and I wanted to go over this activity that we started the other day and kind of wrap it up and tie it all up so that we understand what we're supposed to do with it. So the first thing is we wanted to go through and look at these fish lengths and make a dot plot and find the mean and the median. And so real quickly, I'm going to try and speed this up, but we want to go ahead and draw in the dot plot. And so when I'm looking here, I got 3 and 5 and 6 and 10 and 6 again and then 7, 7 again, 8, 4, 5, 6, 4, 7, 5, 9 and 9, 8, 7, 6 and 8. So there's my data there, and that's pretty unimodal and symmetric. In fact, that's about as symmetric as most data is going to get. So we would describe this as unimodal and symmetric. To put it in context, we'd say the distribution of fish lengths is unimodal and symmetric. We'd also want to describe the center and the spread. Well, we're starting to learn about centers, and both the mean and the median are measures of center. And so if we wanted to look at this, we'd compare what the two are and kind of go with whichever one we feel is best representing the data. But mean is 6.5, and I think the best way to do that is just to go through and add them all up and divide by 20. I think we get a sum of 130 maybe. And then our n is 20. So if I find the mean, or x bar, that's 130 divided by 20, which I'm hoping is 6.5. Okay? And then the median is the median is the middle number. Now, I saw some people trying to write out all the numbers in order from least to greatest, and that's fine. You could do that, but we can also just look at this and kind of say, all right, well, let's count, because we know we have 20. So let's find where the 10th and the 11th one is, and then we'll figure it out. So 1, 2, we'll just pull over dot 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the 10th one is in 6. The 11th one is in 7, so the median is right between the two, and so the median is also 6.5. And so in this case, where it's unimodal and exactly symmetric, the mean and the median are exactly the same, and so it really wouldn't matter which one we use, although we'd probably prefer to use the mean so that we could use the standard deviation a little bit later. Now, going and looking at other data, all right, what happens if we change this 10 right here, or this dot right here, and we make it 15? So I'm going to do this and kind of pull it out, and there's a little bit of an outlier, okay? If we cancel this 10 out and we move it out here, what happens is our sum increases by 5. So now our sum is 135. Our number of items is still 20, and our mean now jumps up to 6.75. So the mean is increasing, 6.75. And that would make sense that the average would go up because we had a number go from 10 to 15. It increased by 5, and so our mean goes up a little bit. The interesting thing is that our median is still going to stay the same, because here's 10, there's the 11th number, and so the median is still 6.5. And so in this case, the mean changed because of the outlier. The median did not. And so that's kind of a little interesting tidbit there. Now, if we took that 10 and we changed the 10 to a 20, so we're going to put this way out here. Now what's going to happen is my sum is 140, n still 20, and x bar, or our mean, is now 7. And so now, when we've taken that number 10, all right, our largest item, and made it even larger, our mean is increased by a half of an inch now, okay? And so the mean's still 7. What happened to the median? Still stays at 6.5. So even if we have that really large number, the median is not affected by that outlier. And so we can go ahead and say that the mean is not resistant to outliers, but the median is resistant to outliers, meaning it doesn't change when we have those extreme values. So that's kind of an interesting point that we want to make. The next thing we wanted to do is we wanted to look at set 2 and set 3. And I'm going to go through and try and do this as quickly as possible so that we get some good data here, and hopefully we'll split it up. But let's first make our dot plot because we always like making the picture. I'm going to make these dots pretty big pretty quickly. So we got a 3, a 5, a 6, a 10, 15, which will lay out here, 7 back here, then another 3, another 3. Oops, those are 3s that are done. Before I put there a 5, a 6, 4, 12, 5, 3, 4, 8, 13 right there, 11, and 9. Okay, good. So if I do all that, there's my dot plot, and I would describe this as saying it's unimodal. The distribution of fish lengths here is unimodal and skewed right, because the tail is off to the right there. All right, and then when I come back over here and calculate the mean, I'm going to go through and I get a mean of 6.8 and a median of 5.5. Now, it's kind of expected that they would be a little different, okay, because it's not symmetric, but this is kind of a big deal. So if I added them all up, I got 136. I divide by 20, and I get 6.8. Let's take a look at what set 3 does. In set 3, if I go ahead and put the points in here, the dots, so we got 3, 5, 6, 10, 10, 7, 10, 8, 9, 5, 6, 4, 9, 10, 9, 9, 10, 7, 10, 8. So this data here, whoops, this data here is unimodal and skewed to the left. So here we say our fish lengths in set 3 is unimodal and skewed, left. Because again, the tail goes out to the left. The median here, or the mean I should say, is 7.75. I think if you add them all up, you get a sum of 155, and n is 20, so that gives us a mean of 7.75. If I go and I calculate where the median is, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 is here in this column, so our median is right there at 8.5. Okay, so we got to look at this and we say, all right, if I'm examining this and looking at the data here, the mean is bigger than the median, so the mean is greater than the median. And in this other one, the mean is less than the median. And that's because of the skewedness. If it's skewed to the left, these lower values are going to go ahead and pull the mean down. And so by pulling the mean down, the mean becomes less than the median. And when it's skewed to the right like this, the higher values are going to pull the mean up. And when that happens, then the mean becomes greater than the median. Think of it in our class example. If we go and we have our class age, and I'm not included, and it's just the students, our mean and median are probably going to be around 17 or 18 years old. If I'm included, I'm 37, pulls the age up, the mean age is going to go up, but the median, the middle age, is still going to be around 17 or 18. If Mr. Kramer walks in the room, then all of a sudden now you have this really, really old guy, and he's going to pull the mean up that much more. And so the mean is going to be greater than the median, and that also goes to show that the mean is affected by outliers, whereas the median is resistant to outliers. So if we go and just kind of summarize what we learned here on this first page about fish lengths, is that the median is resistant to outliers. It doesn't change when you get those extreme values, but the mean is not resistant to outliers. And so when we look at that, that goes into our decision as to which measure of center we want to use. Also, if the data is skewed to the right, the mean is greater than the median, and if the data is skewed to the left, the mean is less than the median. That has another effect on what we want to do. And if the data is skewed, we like using the median simply because it gives us a better representation. You'll hear that when we talk about median incomes or median household prices. All right. If the data is symmetric, the mean is a better measure of center to use simply because we can use the standard deviation. We'll learn more about how that helps later on. So I hope that helps. Watch part 2 to see how the back goes and how we calculate the standard deviation, and then we'll go from there.